material on dyeing and crystallization for National Mission Project on Education through ICT. Additionally, he has conducted hands-on training workshop on topics such as microreactor, advanced flow reactor, and process intensification for MTech and PhD scholar and young faculty. He has spearheaded numerous national and international initiatives, including international conferences on chemical and bioprocess engineering and organized GAIN program on sonoprocess engineering, membrane separation, process and process intensification. Dr. Sonawane sir's profile academic output include over 150 SCI index journal publication, 36 book chapter, and 2 book alongside 25 patents filled with 48 granted patent. His research interests sonoprocess engineering, cavitation-based nanotechnology, wastewater treatment, nanopractice synthesis, and polymer nanocomposites. He has developed indigenous technology for dye water treatment and novel anti-corrosion coating with self-healing mechanism widely applicable in marine and windmill industry. His microreactor based technology for production and advanced dispersion method of nanoparticle have been utilized by ISRO. Dr. Shirish Sonawane sir has received several awards including Vivek Award, DST Young Scientist Award, and Institutional Engineers Award. Sir has more than 4,000 citations. He continues to influence the global chemical engineering community. Dr. Shirish Sonone sir editorial role includes serving on the board of journals such as Nanoscience, Advanced Biotechnology, Chemical and Environmental Engineering, and other. He is also a chief editor of Scientific Journal of Bulletin of SUS Universe series, Food and Biotechnology. His expertise combined with his commitment to innovation make him an extremely leader in chemical engineer and nanotechnology. We are really happy to have you on this session, sir. Thank you. Thank you very much. Now over to you, sir. Thank you, sir.
Welcome, sir. And now I request you to kindly share your screen and start your session, please.
Okay. Hello, Dr. Shirish. Good evening, all.
Good evening, sir.
Shirish. So, basically, thank you for first. Let me thank to Professor Shailesh and the other colleagues from the DY Patil Institute also to inviting me for this ATAL FDP. I think I hope I will have this session related to functional nanomaterials. Before that, let me see some important, uh, details I want to show. Sustainability is what basically before going to the functional materials and to fuel cell. First, let us look to the sustainability. What exactly it means that it is says that uh, we need to be meet the present need without compromising the needs of the next generation. Okay, or the ability to compromise within a future generation. This is very important point that we always been in terms of a grid. We search and utilize the resources very uh, in a greedy manner, and because of that, the problems have now started. Maybe greenhouse gases, if you look, or maybe acid rain is there. These are some of the major challenges that we are been facing. Let us look to an example. Based on that, we can understood. For example, in the smartphone, if you look, there are a number of rare earth metals have been used, and we know that rare earth metals. It meaning is that they are very difficult to separate out from the earth. So, and they are obviously in the limited quantity. So, if you look to the possibility for the next generation, we must need to think that how they are going to be operate with the possibility of a new electronic devices they are going to come up with. Okay, so basically there are three important pillars are there of a sustainability: society, environment, and economics. So these are the three important pillars. These are also very much interlinked with each other, and we need to see that with these three balances will going to be lead to make it to the sustainable society. So in the basic, if you look to sustainable as an engineer, what we should look into the when we are designing any product or any processes we are doing it, we must need to be see that the sustainable engineering design, it should have the basically use of renewable materials, okay, and there is also not just efficient processes, but also we need to be see that there should be a zero discharge also. This is one of the important aspect of sustainable energy is there. And basically energy is become our inherent part of our life, and we required to, as a population is growing on, we can see that the whatever the form of energy we are utilizing it, it could be or maybe chemicals or water we have been utilizing it, we can see that it should not have any kind of waste generation to be happen. Lastly, it is impacting onto the earth. So basically, if you look to the earth as one of the important aspect, only one important word here it is mentioned is an biogenic with a red color. So biogenic means that it is the material, uh, how there is some mechanism with the mother earth to nature to deal with this material. So we call it as a biogenic materials. There are lots of other products are there which are anthropogenic, and we are developing that one. Surfactant, morning soap, starting to the whole day life. If you look at lot of anthropogenic chemicals we have been liberating, which is not been going to be dealt with by the mother earth. So whatever, again there are lot of other issues are there. For example, solar panels are there. That is also nowadays it has came up that can we have the recycling, and obviously the silicon quartz based materials are there, we can able to recycle, and we can panels can be utilized. So this is again the next generation issue is there. So from there we are going to start, though we have been removing the fossil based fuel, but this is also one new generation problem we are going to be addressed. So what I mean to say is traditional design criteria, if you look, there was only three thought processes were there. We will always say that how is the function of that the equipment or cell, what is the cost, and whether the safety is there or not. So, but the new design processes, if you look, there is important that how is the impact on the society, what is the impact onto the environment, and that is the measure the sustainable criteria are there. So design thinking wise, future we must need to be see that materials are whether the energy is a renewable energy, whether it is being produced at a localized way, whether that material is a recyclable, whether the power is being passed through the battery and solar cells, whether it can be recycled at the end, and it is also we need to be see that whether there is any release of the toxic metals are there or not. So if you look to the current ratings, basically refrigeration purchases are there. Chlorofluorocarbons or CFCs have been banned, and usually there's a cooling point of view. The refrigerators we used to be have the cooling chemicals. So now it has been banned. So the now rating was we always see about the energy efficiency. But it is also very important to see what are the releases of heat is there or any toxic chemicals have been released into the environment. So sustainable matrices for the indicators we must need to be see any equipment, fabrication, design, we must see that what kind of materials is there, whether it is recyclable, reused, and can we have this any liberation? Is there a toxic release? Energy use, whether in the form of sustainable energy, how much water quantity it is being utilized. We always looked and linked in terms of the form of what it is called with the relations to the environment. So emissions are there. We need to be see about the about that. So lastly, the one of the possibilities that the fuel cell basically. So let us look to the fuel cell how it is going to be.
Sir, excuse me.
Yeah,
Excuse me, sir. Sir, have you shared your PPT, sir? Participants are asking.
yeah, I have shared. एक minute.
It is not visible, sir.
Oh.
I thought you are yet to share the PPT, so I did not ask.
Yeah. Anyway, it was the introductory part. Anyway, can you see now
Yes.
here this prototype development of fuel cell? Now let us talk about the one important aspect about this one. Is it visible now? Hello?
Yes, sir.
Yeah. So let us see that in the energy station
Yes.
within a fuel cell, can we see about the one? Basically, fuel cell is what? Basically, it converts your chemical energy into the electrical energy. So for that purpose, we need to be see that how it is going to be happen, and the large scale is making it very important. So this one we can do it through the there is an anode cathode, and there is a membrane in between them, and then from there the catalyst is basically the platinum is going to be used. Now for this fuel cell there are major challenges are there, like the catalyst, then one is in a membrane, Nafion membrane, which is a costly, and catalyst is a platinum-based catalyst. We know that it is noble catalyst. The speciality of this catalyst is it is a noble one, so it has the oxidation and reduction, both the reactions. It carries it very efficient way without much poisoning. So these are the effectiveness are there. But let us, if you think that in a fuel cell, let's say whole USA starts using the fuel cell for the automotive industry, and catalyst loading for each single cell, let's say 100 centimeter square, let's say one cell is there. So area is 0.2 to 0.3 milligram per centimeter square is the generalized area it is. Okay. So it is this an area that can have been is going to be very much large quantity it is required, and in such a case the platinum is going to be vanished in very few years, maybe 20 to 15 years. So these are the some of the challenges are there. But let us work out on to the fuel cell how we are going to this useful it is. So basically there are polymer membrane electrolyte PEM membrane fuel cell it is. So in that case it is a low temperature and high temperature, maybe below 80 degrees Celsius, usually the low temperature, 80 to 120 is a high temperature fuel cell. So I have worked earlier only with a low temperature fuel cell, because if you work onto the high temperature fuel cell, the energy utilization will be very much higher, and lastly the our energy outcomes efficiency wise is going to be reduced. There are also mechanical, it is technically complex system, basically the fuel cell it is. It contains the gas has to be flow uniformly onto the surface of this composite membrane, and it should have the distribution also. So in this case there will be generalized targets. If you look, this is the gram catalyst loading is there. Here it has been mentioned 0.3 to 0.6, but currently it has been there 0.2 to milligram per centimeter square. And this was the stack we need to be created. It is not in a single cell. So there were a number of challenges are there in India as well as abroad at the time. Like it is the story of 2014-15. Now we have quite advanced now in the fuel cell is concerned. So the durability of a cell and performance for longer cycle time were the major challenge. As well as I told you, the catalyst 1 plus of platinum, then we have the palladium or nickel based or non-noble catalyst, and loading that going to reduce. So overall, per kilowatt pricing, costing, it has to be get down actually. Okay, so it has to be maybe how many number of cycles, hours it is going to be run, for example. So it is necessary to have improvement in the stack design. So there are number of other challenges were there. There are a number of companies have initiated the existing processes, and there is a transition metal alloy catalyst are there, or maybe the what is called the core shell structure of platinum catalyst is there. It is also been developed in India. BHEL, IITs are working. NMRL, CGCRI, CFCT. These are the main institutions where attempted to have the fuel cell at that time. And through that, we also understood that in the mechanical engineering, flow field design is also very much important. Other people have also added the what is called additives to get it more functionalize the component. So here, Nafion membrane, can we have any other possibility to see that membrane can be we can have the replacement for this Nafion membrane? So existing technologies are still also, if you look, there are some challenges are there. Limited life cycle. This is important into economic consideration. Flow field design, we need to be developed for this development of a pressure, and the overall cost of a platinum catalyst, it is also need to be reduced, and the membrane of an Nafion. So durability of the cell and the cost of the stack, which has to be major barriers in their commercialization. So the side reaction of the catalyst poisonings are some of the problems which are the current catalyst technology is facing. PEM membrane with high mechanical strength and good production conductivity will also is required actually. So catalyst is a low cost, non-noble metal, and which can have the lesser side reactions that we need to be see, as well as we need to be see that loading of the catalyst can we have the reduction. So if you look to the fuel cell, these are the basically assemblies there. Here, these are you can look to the groovings. So it is basically called bipolar plate. Okay, and end plate is the last one. This is also end plate, which is maybe of aluminum, and in between that there is also gas flow channels are there, and then from both the side the channel gases are going to be flow, and these units are going to be repeated. This is your membrane along with what is called MEA assembly. It is called membrane electrode assembly, which is anode cathode, and inside there will be a membrane. So catalyst, we understood that there is a lot of impact is there. What kind of catalyst, how it has been prepared, that is also been impacting onto the overall performance. What are the in the catalyst also? What are the what is called impurities? They are also been impacting. There is also the commercial grade carbon. It has been available, which is contains the 40% of catalyst platinum, and other is a carbon. Nowadays we get a graphene also as or graphite also as a part in which we can have the carbon combinations. We can able to use it, and based on that loading we can able to carry out. So one attempt also we tried to make it to can we use the reduce graphene oxide RGO, and based on that the on that one can we add these metals, noble metals, to have this combination. So high ionic conductivity is also is required, and that ionic membranes are will required to be have this conductive proton exchange membrane to be making it this nanocomposite. So we had the expertise on the PIM what is called onto ultrasound cavitations, and we thought to we can utilize the catalyst synthesis also using the cavitation based processes, in which 20 kilohertz uh, frequency cavitation is being sent into the liquid, and then it will have this what it is called going to be how catalyst uh, uh, synthesis we can carry out, as well as the membrane encapsulations are also going to be possible to be utilized. So here is a design of a flow field design is also I'm going to show you how we have formulated the uh, plates. So it is overall it shows that the catalyst basically PEM fuel cell with one maybe 100 200 wattage generations we are been we are trying to making it to be have that attempt. Let me go through the fuel cell again if it is. So one of my student was there, Rajesh. He is now in the Reliance working with other with an graphene-based energy-related, utilization of a composites only. So in that he also attempted, during PhD his work. He has fabricated and catalyst synthesis. He made it using the what it is called ultrasound assisted method. So you can see the again components. These are the end plates. There will be, it is called as a current collector also. There will be gasket. This is ME assembly I told you, and there will be a gas distributor, or onto the gas is being distributed over it. Okay. So basically Rajesh has tried to replace the platinum using the cobalt and nickel, because as I understand, you can understand that cost is very high, so we can able to reduce the overall cost of this one. So here is in place of literature we will go to. So basically, if you look to the synthesis of ultrasound, if you look, there is advantage. We can have the higher reaction rates basically, and you will getting the less impurities in the form. Then you will have the mono and bimetallic particles are there, and there will be a lesser ripening also, and overall reduction in the reaction time, and you will have the overall morphology we are going to get it. So here, if you look, this is the platinum-based nanoparticle synthesis are there. In this one, ultrasound is there in the during the sonication time. You will have the carbon addition. Then we can that carbon or graphene will have what it is called nucleation is going to take place, and then on that one these small platinum catalyst particles we can able to make it. So basically preparation of the membrane electrode assembly, we need to follow a very specific process. Let's say you have this what is called membrane is there. From the top you can have the carbon paper or maybe carbon cloth, on which one side you can coat it with the catalyst ink. From the other side, we can also have the coating with the catalyst ink, and then we can press, and hot press is the MEA membrane, and from there you can have the MEA preparation to make it. So you can see that anode side gas diffusion layer is there, Nafion, and cathode side gas diffusion layer, and then we can have this preparation. So this is basically TIM images are there of a platinum carbon material. You can see it. The sizes are in very quite smaller with NaBH4 as a reducing agent, and this catalyst which has been utilized. So active surface area is quite good for that catalyst which has been prepared with the platinum and carbon. As I told you that commercial prepared will have the 40% PT carbon, will have this other, and 40% PT carbon commercial will have the better surface area. So this is the possibility, and based on that we can have the higher surface area catalyst. Now you can look to the overall performance here. If you see that 0.2 wattage per centimeter square is the output for the one, and with the 5 cell, it was possible to attach complete fuel cell stack over there. So now here it is some other catalysts also been attempted, platinum and cobalt. This is basically a bimetallic catalyst to which you have this partial cathode side, 25% of the platinum is been replaced. So here, some of the XRDs you can see over here that cobalt has been added. Now, this is also shows the very good active surface area, which is around 8.7 meter square per gram, and electrode, and with the current density which increases with the addition of cobalt for this oxidation reduction. So fuel cell performance wise, if you look, it has a 0.35 watt per centimeter square. It is comes to 0.25, and then it is has the 0.6 to 0.8. It will be there. XRDs are also are there with you can see here the replacement of a cobalt with a platinum. It has been replaced from 17 to almost 50 to 17. Okay, so from there we can have this overall. You can understood that there is an cobalt content. If it is reduced, the intensity is again increased, and then there is structural difference is there. But they have been successful to replace it almost 25% of the platinum replacement. That is also very much value addition it is. Now I will show you the other methodology. This is one way of obtaining this platinum catalyst. Now actual fuel cell, if you look at here, it can be shown like this. For example, there are number of parameters are there which are been affecting onto the performance of this stack. Actually, they are maybe operating temperature is there, pressure of the reactant is there, humidification, cooling is there, and leakages of these plates are there. So because of lesser humidity of that one, you will find that there will be burning of MEA is there. So if you don't have humidification or leakages are there at the end plate, so we need to be maintain proper pressure. There is also need to be see that water formations we need to be removed, maintain the consistent flow rate also, as well as we need to be provide cooling on the both the side, anode and cathode side. So in our case, as I told you that we have completed the components for the fuel cell stack. You know, you can see here there are the plates are there at the inside. You can see over here. These are the carbon plates are there, graphite plates. Both are they are different. This is cooling channels are there. and these are the end plates are there. Okay, so these are been very small grooving. It is been happen. Here you can see this is the stack we have fabricated using the for the using the catalyst of what it is called of a platinum using the fuel cell. So there is a grooving, and then based on that we are coating it, and then from there we can have this uh, test station, and then stack is been created. So this is overall one possibility that how stack can be prepared actually. So there are it is optimization, number of optimizations we need to be carried out, specifically cell temperature, humidification temperature, and oxygen and hydrogen, flow rate. So these are 2,500 centimeter cube is the flow rate is there per minute. And here is also there is for example, wattage is there 160. For example, if you look that you will get it the wattage around from the 160 with current of 70. So it is overall good output. It is for the fuel cell is there for the 40%. Okay, so um, the this area, if you look for the single cell, it was in 100 centimeter square area, and from there we have been carried out. There were also other issues were there. For example, uh, uh, mm, making the increasing the temperature, your overall performance is also decreasing. Power wattage we need to be see that we can have that 180 to 200. So this is the PEM fuel cell cathode is there. Okay, this is 160 to 180. We can have reduced. So these all optimizations have been carried out. So there are certain important conclusions are there that fuel cell stack with the OCP need to be seen that should have the impact, as well as that OCP is observed around 4.85 voltage for 5 cell stack and 0.97 for each cell. And we have this observed that output. Now, 5 cell stack temperature optimization of hydrogen air is 60. S2 airliner heater temperature is 65, cell temperature is 50, flow rate is hydrogen gas is 2000 and air is 8000. In place of air, in place of hydrogen, if you oxygen, if you use an air, then you can understood that there are a lot of fluctuations are there of because onto the performance. The reason is that we have 20% is only oxygen in air. So there will be deficiency. So it is a starving effect. It is, and because of that, there will be a lot of fluctuations are there. So these are the some of the voltages are there for platinum, cobalt, voltages, and from there we are getting these outcomes of PEM fuel cell. So this is related to the final form. If you have the some designs, let me show. Here, you can see some, I will show you. Sorry. So these are some of the dimensions are there of the plate. This is end plate dimensions. You can get an overall, understanding that how it is happening. So this is end plate dimension. If you see, these are the polymer gasket dimensions. Okay, these are, you can understood that it is just 4 mm. It's very 1 mm smaller, grooving it is there. On this is anode side for the graphite plate. It's very difficult to maintain, as well as the gasket is there on these holes actually. You can see over here. This is also a cathode side plate, graphite plate is there, and you can see there are certain details are there. And so coolant is one of the important part in the fuel cell, and it is uh, basically it has to be properly flow. Without that, otherwise there will be membrane starving will be there of gas, and there will be issues. So these are some of the details are there about the fuel cell stack that what we have been shown. And with the help of 10 by 10, almost 100 centimeter square, it has gives you the almost 200 wattage power output in terms of current, with the current of 80 is concerned. Okay, so with this, I have other one work actually to go. So I'm just closing this session. Other things are there related to the PEM fuel cell that uh, with them with we tried with an micro reactor also for the synthesis. I will just show you some glimpses actually within a micro reactor, where Dr. Prashant is also one working on the one of the catalyst based company in the Bangalore actually, which is related to this uh, company for synthesizing this catalyst for energy related one. So he attempted this microreactor based on assembly for synthesis of catalyst. So it is the microreactor through which this catalyst synthesis has been carried out. And initial attempt he made with an iron base, but it doesn't work well. So in place of that, platinum and palladium he initially targeted, and from there he got a lot of good outcomes. Then after that, he also tried with what it is called uh, continuous flow for microreactor, and then from there PT with a uniform distribution is attempted. We got that one, and polyol and other methodologies is attempted. The idea was directly we can use the liquor and utilize it for the directly as an ink, and it is partially conductive ink. It has been working. So this is overall my views are there. I had the videos, but now I think it's very difficult to show now. So this is from overall from my side, Shailesh. Yeah, thank you.
Yes, sir. Okay. Now, I request if participants are having any question, you can please ask. Dr. Shirish is available. You can please ask your questions. Participants, yes, any question?
It was just an in-house development of it was there. Okay.
Any question from any of the participant, you can please ask. Any question?
Yeah, okay. If you don't have questions, so I will just put up my email onto into
Yes,
chat,
sir.
so you can be in touch with me. Okay, my name is Shirish. So you can have Shirish at nitw.ac.in. I am very much interested to have interact with you, but unfortunately, I have the today PRG one project review meeting was there. I will again. If you have questions, you can directly contact with me. Okay. Thank you very much. Yeah.
Sir, now I request Mr. DP Deshpande to propose the vote of thanks for this session.
Okay, thank you, sir. It is my great honor and privilege to propose a vote of thanks on this special occasion. First and foremost, I would like to extend my deepest gratitude to Dr. Shirish Sonawane, sir, Professor and Head of Department of Chemical Engineering at NIT Warangal, for delivering such an insightful and enriching session during 1 week online ATAL faculty development program on sustainable practices in energy and environment sector, organized by Department of Chemical Engineering, D.Y. Patil International University, Akurdi. Sir, your knowledge, expertise, and engaging presentation have truly enlightened us and provide valuable perspectives. Thank you, sir, for delivering the talk. Thank you, one and all.
Now, a small announcement to all the participants. The next session is going to start exactly at 7:30. Because of some urgent and important work, Professor Shirish has concluded his talk very fast. Uh, you all are requested to join onto the link that will be shared to you for the 7:30 p.m. session. Okay. I repeat, the session will start at 7:30 p.m. The next session. Okay. Now you all can leave this meeting, and I request Deshpande sir to close the meeting.
Yeah, thank you, sir.
Thank you so much.